One of the most fascinating things I've talked about with some incredibly smart people is quantum computing. It's a whole new level of technology. There's this quantum computer developed by Google that can solve problems in seconds. Problems that would take regular computers thousands of years to figure out. It's hard to even understand how fast and powerful this is. Some problems would take longer than we can even imagine to solve, but a quantum computer can do it in just 15 minutes or even less. What makes it even more interesting is how it works. The way it was explained to me is that quantum computers might be getting answers from different universes at the same time. That sounds crazy, and even the scientists don't completely understand it yet. But the power of these machines is something the human brain can't fully grasp. The numbers involved are so big, you can write them out, but still not really understand them. This could be the biggest technological breakthrough in human history. And most people don't even know it's happening. I once came across a video, maybe on YouTube, where a very smart kid was talking about how he believes the CERN experiment, where particles were smashed together in the Large Hadron Collider, actually destroyed our universe in 2008. He said it created some kind of powerful atom that caused a massive reaction. According to him, we now live in a nearby parallel universe. He also explained the idea of infinite parallel universes in the first 20 minutes of the video. It's a lot to take in, but the kid clearly understood what he was talking about, and his dad or a close relative was filming him. He claimed that when CERN did its experiment, they made a particle that was too heavy and it broke the universe. Instead of just disappearing, we shifted into a slightly different version of reality. A parallel universe. It's a wild theory, but it makes you think about how little we really know. Quantum mechanics is very hard to understand, but let's try to break it down. Think about something tiny like an electron. Before quantum mechanics, people used classical mechanics, like Newton's laws, which said everything had a clear position and speed. You could predict where things would go and how they'd move. But quantum mechanics changed that. It showed us that, at a very small scale, things don't behave in the way we expect. In classical physics, an electron is just a tiny particle with a position and speed. But in quantum mechanics, it's more like a wave. This is called a wave function. The electron isn't in just one place until you look at it. It's spread out in different possibilities. It follows something called the Schrödinger equation, which lets you predict its behavior, at least to some extent. But here's the weird part. When you observe or measure an electron, its wave function suddenly changes. It collapses into one specific state. Scientists call this the measurement problem. Basically, there are two different rules. One for when you're not looking at the electron, and another for when you are. And no one fully understands why or how it changes when you measure it. This is where things start to sound like science fiction. What does it mean to observe something? Does it require a human mind? Can a video camera do it? Just measuring something can completely change it. That's why this part of physics is so mysterious and often leads to philosophical questions. To make it simpler, instead of focusing on where an electron is, let's think about how it spins. An electron spins like the Earth does. And just like with its position, we can't say for sure how it's spinning until we measure it. But the moment we do, the result snaps into place, and that action changes everything. Imagine an electron as a tiny spinning top. When you want to measure how it's spinning, you can send it through a magnetic field. Depending on how it's spinning, it will either be pushed upward or downward. We call this spin up or spin down. There's no in-between. This isn't just theory, it's something we've observed through experiments. So one basic idea in quantum mechanics is that particles like electrons can only give you one of two results when you measure their spin, either up or down. For example, if you use a magnetic field that's pointing up and down vertical, and the electron is deflected upward, we say it has spin up. Now that we've measured it, we know what state it's in. If we send it through another vertical magnetic field, we'll get the same result again, spin up. Nothing changes because we're measuring it the same way. But here's where things get strange. If we now send the same electron through a magnetic field pointing side to side, horizontal, suddenly the result is unpredictable. It might get deflected left or right, with a 50-50 chance. And after that, if we again try measuring it vertically, the result is back to being uncertain. It could be spin up or spin down, again with equal chances. So even though we knew what state it was in before, changing how we measure it seems to change the outcome. That's one of the mind-bending parts of quantum mechanics. It's not just that we don't know what will happen, it's that the outcome is fundamentally uncertain. This leads to the idea of the universe being like a simulation, similar to a super-realistic video game that feels so real, you forget it's not. This is where the theory of simulation comes in. It suggests that our entire reality might be a kind of computer program. As I explored more about quantum physics, especially weird effects like how observing something can change it, I started to notice how many world religions say similar things, that reality might be an illusion. So this idea grew stronger. Maybe we're living inside a simulation or a type of multiplayer video game. But that raises the next big question. Who built the simulation? There are two main ideas in simulation theory. I teach this in a class at Arizona State University, where we bring together science fiction, religion, philosophy, and technology. One version is called the NPC theory. In video games, NPCs, non-player characters, are just programmed characters. They're controlled by the game, not real people. If this theory is true, we are all NPCs, just part of a very complex simulation. The other version is the RPG theory, short for role-playing game. In this case, we are real beings outside the simulation, and our bodies here are just characters we control in the game, like avatars in a massively multiplayer online game, MMORPG. Just like in today's video games, both player-controlled characters and NPCs can exist side by side. That means both theories might be true at once, with some people being players and others being part of the program. If we ever reach the point where we can build perfect simulations ourselves, what I call the simulation point, that would be a kind of technological singularity. The term singularity was originally defined by a computer scientist turned science fiction writer, Werner Ving. He said it's the point where technology grows so fast that life as we know it completely changes. For example, if we create superintelligent AI or hyper-realistic virtual worlds, things might never be the same again. Now, back to quantum computing. This is where things get even more bizarre. The chip that powers a quantum computer is extremely small, about the size of a saltine cracker. But everything around it, the cooling system and protective layers, is massive and complex. That's because the chip has to be kept incredibly cold, even colder than outer space. It must be sealed off from any outside interference like radiation or radio waves. Even a small signal could cause errors. One of the people leading quantum research at Google, Hartmut Neven, said something astonishing. The power of their quantum chip supports the idea that our universe might be just one of many, a multiverse. According to him, the chip might actually be tapping into parallel universes to finish calculations faster. This idea, while sounding like science fiction, caused quite a buzz. Google's stock even went up because of this breakthrough. But even though it's exciting, this technology is still in the experimental stage. We won't see it in phones or personal devices anytime soon. But still, how did scientists even figure this out? Who imagined that electrons might not just be spinning one way or the other, but actually be in both states at once? This concept is known as superposition. It means that before we measure an electron, it can exist in multiple states at once. It's not that we're missing information. It's that the information simply doesn't exist in a definite form until we look at it. When we do measure it, it collapses into one of the two possible outcomes. This is how quantum mechanics is taught in textbooks today. In the textbook model, you have a wave function for an electron's spin. That wave can be a mix of up and down. But when you actually measure the spin, you only see one result, either up or down, not the wave itself. It's just like when we try to see where an electron is in space. The wave function gives a cloud of possibilities, but once we observe it, we only see it in one place. Some physicists believe there's a better explanation for all this, the many worlds theory. This theory says that when we observe something in quantum mechanics, every possible outcome happens, but in different universes. So if an electron can spin up or down, both things happen, but in separate branches of reality. We just happen to be in the one where we saw it spin up. Quantum mechanics forces us to rethink what we know about reality. It's not just about particles and waves. It's about questioning the nature of existence itself. A small piece of uranium is radioactive, meaning it gives off energy in the form of particles. If you place it inside a bubble chamber, a special container filled with liquid, you can actually see the tiny streaks these particles make as they leave the uranium. These streaks show the path of the particles, especially electrons, that shoot out from the uranium. Now, when no one is observing the electron, it follows the Schrödinger equation, a rule in quantum physics that predicts how particles behave. When a radioactive atom releases an electron, scientists use this equation to predict the electron's path. According to quantum theory, the electron's wave function, its mathematical description, spreads out evenly in all directions like a sphere. That means the electron could go anywhere. But here's the weird part. Even though science says it spreads out in all directions, when we actually look at it, it appears to go in just one straight line. This strange difference between prediction and observation is one of the central mysteries of quantum mechanics. To answer your question, no, the shape of the uranium doesn't affect the electron's direction. The electron comes from one tiny atom inside the uranium, and that atom acts alone. In theory, the simplest and most natural thing for the electron to do is to move out evenly in all directions, but that's not what we see when we observe it. What we see is just one specific path. This tells us something important and mysterious. The way a quantum object behaves when we're not looking is completely different from how it acts when we observe it. Back in the early 1900s, scientists had just begun to explore these strange ideas. Even now, quantum mechanics is a difficult and sometimes confusing subject. Some scientists feel we haven't yet discovered all the answers. They believe we just need better tools, better equations, and more time to figure it out. Albert Einstein is one of the scientists who didn't fully accept quantum mechanics. The title "Something Deeply Hidden" actually comes from a quote by Einstein. As a child, he was fascinated by a compass and wondered how it always pointed north. Instead of just thinking it was cool, he questioned what force made it do that. He believed that something deeper, something invisible, must be guiding it. That same curiosity shaped his views on quantum physics. He thought the current understanding was incomplete and believed there had to be more to discover about the true nature of reality. There are different interpretations of how quantum mechanics works. One of them is called the many worlds theory. This theory suggests that instead of the wave function suddenly changing when we look at it, as the standard Copenhagen interpretation says, what actually happens is that the universe splits into multiple versions. So if an electron can spin in two directions, up or down, then when we measure it, the universe splits. In one version, you see spin up. In the other, you see spin down. According to many worlds, you yourself are also a quantum object. You have a wave function too, because you're made of atoms. So, when you measure something, you and the object you're measuring both become part of a bigger system, and your reality splits. Another key concept is entanglement, which Einstein helped describe. It means that two particles can be linked so closely that knowing something about one automatically tells you something about the other, even if they're far apart. If two particles bounce off each other, their paths become connected. Measuring one instantly reveals information about the other, even if you haven't touched it. This leads to the idea that if science could open a door to a parallel universe, they probably would try it. That's part of what makes the show Stranger Things so interesting. It's based on real, strange ideas. Reality can be bizarre, and quantum physics proves that things aren't always what they seem. Switching topics slightly, it's strange that some people still dismiss climate change, even when there's clear evidence. For example, Iceland recently lost a glacier that had existed for decades. Pictures from the 1980s show it clearly, but now it's gone. Even if we don't blame humans, it's hard to ignore that something serious is happening to our planet. Now, let's talk about something even more futuristic: artificial intelligence and virtual reality. AI is getting smarter very fast. We're already starting to create brain-computer interfaces, like what you see in the Matrix or from Elon Musk's Neuralink. These systems are early steps toward what some experts call the simulation point. This is when technology becomes so advanced that we can create a virtual world that looks and feels exactly like real life. In these simulations, the characters, controlled by AI, would be so lifelike, we wouldn't know whether we're talking to a real person or a computer program. If we're getting close to that now, imagine a civilization that's 1,000 years ahead of us. They would have already built these simulations. In fact, there's a theory that says we might already be living inside one of those simulations without knowing it. That's why some experts believe there's a high chance we're not in the original physical world, but in a digital one created by advanced technology. One of the most powerful tools helping us get closer to this future is Google's quantum computer called Willow. You might have heard different numbers about how many qubits, quantum bits, it has, like 48 or 105. The correct number for Willow is 105, but confusion comes from comparing it to other types of machines that work in different ways. Willow is special because it's a gate-based quantum processor, which means it's very flexible and can run many different quantum programs. It's like the quantum version of a regular computer, rather than a machine made for one specific task. Willow uses a 2D grid where each qubit is connected to its neighbors. This setup helps with error correction, which is one of the biggest challenges in quantum computing. The machine operates at an incredibly cold temperature, colder than outer space, so that electrical resistance disappears and quantum effects can take over. Each qubit is a tiny circuit made to be very stable and reliable. But the real magic happens with something called the surface code. Instead of relying on one qubit to store information, Willow spreads that information across several qubits. It's like having multiple backups of a document so that if one part gets damaged, the information isn't lost. Building Willow was an engineering challenge. The machine had to be protected from heat, light, sound, and anything else that could mess up its fragile quantum state. The control system had to be extremely precise, like a giant orchestra where each instrument must play perfectly in time. Even the software was complicated, needing a whole new way to write code that fits with how quantum mechanics works. The biggest breakthrough from Willow wasn't just speed or power, it was error correction. Until now, quantum computers have been unstable. Their qubits would lose information quickly, like trying to do a math problem while someone keeps erasing your work. Google finally created a logical qubit that's made of many physical qubits working together. This logical qubit lasted 2.4 times longer than the best single qubit on its own. That might not sound huge, but it's a major turning point. It means that for the first time, we can control quantum systems well enough to begin building truly reliable quantum computers. Google's new quantum computer, named Willow, has completely changed how scientists think about the future of computing. Until recently, the more parts you added to a quantum system, the more errors it would produce. This was a major problem, because quantum computers rely on fragile components called qubits, which are extremely sensitive to even the smallest disturbance. If one qubit makes a mistake, the whole system could fail. But Google found a new way to fix that. They used a method called a surface code, which cleverly connects 101 physical qubits in a special pattern. Instead of each qubit working alone, they now work together to support one stable, logical qubit. This is a big deal because it means that even if individual parts are weak, the system as a whole becomes stronger and more reliable. Think of it like building a house out of crumbling bricks, but arranging them in a way that makes the entire house stronger than any single brick. This new way of arranging qubits allowed Google to do something incredible. They were able to correct quantum errors in real time, something researchers have been trying to do for decades. It's like finally building a powerful engine that doesn't misfire every few seconds. This means that quantum computers like Willow can now be both powerful and reliable at the same time. That's a big step forward, because it opens the door to solving real-world problems that classical computers simply can't handle. One of the most amazing things Willow did was a task called random circuit sampling. It's a special kind of test where the quantum computer runs a bunch of random operations and records the results. This might sound like just a technical trick, but it's actually a major milestone. Why? because it proved that Willow could do something in under 5 minutes that the world's fastest supercomputers would take 10 septillion years to complete. That's a 1 followed by 25 zeros. Far longer than the age of the universe itself. This wasn't just about speed, it was also about reliability. Previous quantum computers have done fast calculations, but they made too many mistakes to be trusted. Willow, thanks to error correction, gave consistent, accurate results. And that's exactly what scientists and engineers need to build practical applications, whether it's in chemistry, medicine, or artificial intelligence. Some people misunderstood what Willow's breakthrough meant. There were wild claims about it opening doors to parallel universes or proving the multiverse. But leading scientists quickly clarified that Willow's success doesn't prove or disprove any theory about multiple realities. It's simply a huge step in computing power, not a discovery about the nature of the universe. Physicists explained that Willow's test was designed to be very hard for classical computers on purpose. That's how they were able to clearly show quantum advantage. It's similar to how the Wright brothers didn't fly across the ocean on their first flight, but they proved that powered flight was possible. Willow might not solve climate change or unlock every mystery of the universe, but it proves something just as important, that we can build quantum computers that work, and that opens the door to an entirely new era of technology. Most quantum physicists agree that everything Willow, Google's quantum computer, has done can be fully explained using well-known principles of quantum mechanics. There is no need to believe in new kinds of physics or hidden forces. Willow simply uses better engineering and smart design to do what quantum theory has always predicted. One key concept in physics is called Bell's theorem. It rules out the idea that quantum particles are secretly following unknown rules or being controlled by hidden forces we can't see. Scientists have tested Bell's theorem many times, and every result confirms that the strange behaviors we observe in quantum systems are not caused by something hidden. They're just how quantum physics really works. Willow followed these same rules exactly. Each qubit, a basic unit of quantum information, acted exactly as the theory says it should. Some physicists, like Scott Aronson, have said that if there really were hidden variables controlling quantum systems, then those systems should be able to solve problems that normal quantum theory says are impossible. But so far, no quantum computer, including Willow, has done that. This proves that quantum mechanics still holds up, even as we push it to new limits. What makes Willow special is not some mysterious connection to other universes. It's the incredible level of control it gives us over quantum systems. Willow showed that with careful engineering, quantum computers can work the way scientists predicted, and they can be powerful enough to do things classical computers could never do. This isn't just a theory anymore, it's real. Quantum mechanics has been one of science's most accurate and reliable theories for nearly 100 years. It has helped us understand how computers work, how stars shine, and even how atoms behave. But until recently, some of the more advanced predictions of quantum theory were impossible to test because we didn't have the right technology. Willow is helping change that. For the first time, we're testing quantum mechanics on a much larger scale, and everything still matches what theory predicts. There's no sign we need new physics or alternate realities to explain what's happening. This doesn't mean that ideas like the many worlds interpretation are wrong. It just means Willow's results don't prove or disprove them. Those ideas are still more about how we think about quantum mechanics than things we can test directly. What truly excites scientists is how Willow moves us closer to building practical, fault-tolerant quantum computers. That means computers that can work accurately even when small errors happen, something essential for real-world use. These future machines could change everything from how we find new medicines to how we design materials or improve artificial intelligence. While some people are drawn to science fiction ideas like parallel universes, the real story of Willow is even more amazing. It shows that humanity is starting to truly master quantum systems, and that skill could reshape our world in powerful and practical ways. Even though Willow didn't open a portal to other dimensions, other quantum experiments are exploring the very nature of reality in fascinating ways. For example, in 2022, researchers at Caltech used Google's earlier quantum processor, Sycamore, which had 53 qubits, to simulate a quantum wormhole. In simple terms, they made quantum information appear to travel through a kind of wormhole, like a shortcut through space. It was a simulation, but it showed that quantum computers can help us explore ideas that were once only possible in advanced theory. This experiment tested something called the AD/CFT correspondence. It's a theory that suggests our 3D world might actually be built from information stored on a 2D surface, kind of like a hologram. It's similar to the idea behind the holographic universe theory, which says our universe might be like a very advanced 3D movie projected from a flat screen.